Hi, I'm Zhe Li from the Hong Kong Polytechnic University. We are the authors of the paper Polyfit, Polynomial-Based Indexing Approach for Fast Approximate Range Aggregate Queries. In this work, we study how to use polynomial functions to answer approximate range aggregate queries. Range aggregate queries are very common and have been frequently used in OLAP systems. In recent years, its application has become wider. For example, in geo applications, one may interest in how many restaurants in a given region or what is the average price in this given region. And in financial applications, one may interest in the minimum or maximum values within a specific time interval. Consider the huge amount behind these applications. It's reasonable to further improve the query response time of range aggregate queries, though it has been studied for a long time. So, inspired by the recent prosperity of range index studies in database community, we think using function approximation to answer approximate range aggregate queries could be helpful in improving its efficiency. So let's consider this example. Here we have a financial index called Hong Kong 40 index, which is given in the form of time value pairs. Then to answer a range sum query, we can simply generate its cumulative function, then use subtraction to retrieve the range sum. However, since the cumulative function should have the same amount of pieces as the original time value pairs, it may not be very efficient. To improve the efficiency, we want to use a much less complex function to approximate the original piecewise cumulative function. So here, the red line is the generated cumulative sum function, and the blue dashed line pk represent the approximation of it. Then we could use the approximation function p to retrieve a similar result, but it will be much faster. Similarly, to answer a range max query, we can first generate the corresponding max function as a guangshu, then approximate it with a simpler function. After that, we can use mathematical tools such as derivatives to quickly answer the range max. However, using function approximation to answer range aggregate queries will always have some errors. That's why we focus only on providing approximate result for range aggregate queries. Here, we formally define our problem as follows. A user can provide an absolute error threshold or a relative error threshold, such that the return approximate range aggregate query result should satisfy the given error thresholds. Take the previous sum query, for example. If we use the generated cumulative sum function to get the corresponding cumulative sum of L and U, then we could use CF2 minus CF1 as result. This result should be the guangshu. However, if we use PK to approximate the cumulative curve, which is the blue dashed line here, and we use PU minus PL as result, we will have an error, right? Then we either directly want the error less than a threshold, or we want the relative error less than a threshold. The former from our problem 1, which is QABS, and the latter is our problem 2, QReal. To solve the problem, we propose our index framework called Polyfit. Here we show its construction framework. We first divide the desired query type into two, count sum or min-max. For the former, we generate key cumulative function curve. For the latter, we use a key measure curve, which is just a continuous version of the original key value pairs. Then we could use polynomial functions to approximate this curve, and finally organize the generated polynomial functions by a general index structure like B plus tree. One may wonder why we use polynomial functions to approximate the curve. The reason is we found that polynomial functions could be more suitable in our problem settings. But to our surprise, it hasn't been used in any previous learning index structures. In our case study, we found that the model evaluation time of lower degree polynomial function is very close to a simple linear function such as linear regression or linear segment. And all of them are much less than a simple neural network like 300 units, 300 layers, or each with maybe 20 units. And however, when compared with approximation ability, the maximum error of polynomial function trained by our method is close to the neural network, and both are better than linear functions. In addition, For neural network, it's hard to train it to satisfy a given error threshold without using post-checking and replacement, as what has been done in RMI. But those final models may no longer be a neural network anymore. It could be a B+ tree, right? So here is the right is our example. The red curve represents the continuous max function of the Hong Kong 40 financial index. Then we use a degree 4 polynomial function to approximate the curve, which is represented by the blue dots. And it's obvious that this approximation is much better than using linear regression or linear segment, as shown by the orange and green dashed lines. Notice a degree 4 polynomial function only takes 5 parameters. However, to achieve the same error, one may need at least 3 linear models, which takes 6 or more parameters. So how to use polynomial function to approximate the curve? Traditional approximation techniques such as polynomial regression may fail to fully utilize the usage of error budget. And previous segmentation techniques may also not be ever available here in our scenario. We hence propose our own methods to solve these challenges. The result is Polyfit could use the least number of polynomial functions to fit a curve for a given maximum degree. Please check our paper if you are interested in the details. After we build a polyfit index structure, we can execute the range aggregate queries. This figure shows us the query framework. For a query with its key constrained by a lower and upper end, we first use the index to find the corresponding polynomial functions that cover them. Then we use those functions to get the prediction values and process them to get the approximate query result. Notice if the error threshold is in the form of relative error, we still need to test some error conditions. And if it failed the error conditions, it means it cannot satisfy the relative error and a refinement phase must be conducted to find the exact result. Specifically, for count and sum queries, we just do the subtraction using the prediction from our polynomial functions. For min-max, we use derivatives to efficiently retrieve the local minimum or maximum and compare them with the min-max between these two ends, which could be efficiently found with an aggregate tree structure. For how to efficiently check the relative error or combine polynomial functions with aggregate trees, please check our paper for the details. Note that all of the previous discussion only focus on single key range aggregate queries, so that's the existing learning index structures. But in this work, we also extend our techniques to 2 keys using similar ideas. For example, we still use polynomial function to approximate the cumulative surface, and then we use prediction from functions to answer approximate range aggregate queries. Now we briefly check the experimental result. So we compare Polyfit with both existing learning index structures and other range aggregate query methods, including sampling, histogram, approximate query engines, machine learning based approximation, and time series database methods. We use 3 datasets in the experiment to test the performance ranging from 1 million to 100 million of records. On single key performance, we first compare with the methods that can provide absolute or relative error guarantees. We vary both of these thresholds to see the performance change. So the result is that we could be 1.3 times faster than best competitor in single key count query and 2 times faster in single key max query. When compared with range aggregate queries methods that cannot provide absolute or relative error guarantees, Polyfit can still provide a better error and query response time trade-off than all the competitors. Lastly, we compare space-time trade-off with competitive learning index structures. And the experimental results show that Polyfit can still have a better space-time trade-off than PGM and fitting tree. So, in conclusion, we propose a polynomial function-based index structure called Polyfit, which minimizes the number of models required to approximate the curve. We use Polyfit to answer approximate range aggregate queries with 1 or 2 keys with absolute and relative error guarantees. Experimental results show that we can provide faster query response time and smaller index size. That is 1.3 times faster in single key count query, 2 times faster in single key max query, and up to 2 orders of magnitude faster in queries with 2 keys. That's all. Thank you.